All right, I'm going to start. Okay, today I'm going to do some reviews of previous chapters. We'll begin with chapter 9. I'm anticipating the test, which will be December the 4th. Okay, that will cover chapters 8, 9, 10, 11, and 14. Okay, the chapters on spectroscopy, okay, those are going to be tested over next semester. You'll have spectroscopy questions embedded in your exams next semester. Okay, so I'm waiting just a couple more minutes for some others to join. Okay, going to go ahead and start. Okay, I'm going to write a question on the board, and I'll wait a minute or so, and then I'll give the answer. Okay, this will benefit you the most if you attempt to answer the question. Don't simply wait for the answer. Okay, we're going to start out with chapter 9. I'm going to have some nomenclature questions. Okay, first one is 4-phenyl. Pent 1-ine. 4-phenyl pent 1-ine. Okay, I'll give you a minute to draw that. Okay, pent 1-ine. Yeah. Okay, so this is 4-phenyl pent 1-ine. Okay, 1-cyclopropyl octa 1,4-diine. Okay, if you can, maybe you could display the hand raise signal when you've got it. That way I know if I'm allowing enough time. One cyclopropyl octa 1,4-diine. Okay, so octa would be 8 carbons. And we have 2 triple bonds, diine. Okay, one of them is between 1 and 2. The other one is between 4 and 5. So 1, 2, 3, 4, 5. And then we'll have a cyclopropane instead of an H at this position. Okay, next one is trans. One, 3 diethynyl cyclohexane. Right, cyclohexane, 1,3-diethynyl. Okay, ethine is C triple bond C. Okay, and then to make it trans, one would be forward and one would be back. So show me the mechanism for this reaction. I've got propine, and we're going to react that with Na, NH2.
Wait, Dr. Trump, what's the compound below the liquid compound? Is it NH3?
NH3, yeah, liquid ammonia, it's a solvent.
All right.
All right, this is an acid-base reaction. The main idea here is that terminal alkynes are unusually acidic for hydrocarbons. Okay, this is the base. It's the conjugate base of ammonia. Okay, so this will take this hydrogen. This pair of electrons will then move on to the carbon. Okay, so this is the conjugate base of the alkyne. Sodium is just a spectator, so just leave it alone. And NH2 minus then becomes a solvent molecule. Okay. Let's take this and react it with cyclohexanone, followed by acid hydrolysis. Okay, think about the Grignard song. This is very similar. It's not a Grignard, but it's the same type of reaction. Okay, the carbonyl is polarized, carbon end is plus. Nucleophile will attack the carbon nucleus. Okay, so we'll we'll form a new carbon-carbon bond. And then in the last step, we'll pick up an H. And our final product is this acetylenic alcohol.
Can you leave that last part up for just a minute more?
Yeah. Okay, so we have okay. Okay, got it?
Yeah, I got it.
Okay. Okay, for this one, just draw the product, not the mechanism. Okay, so we've got but2-ine. Two equivalents of hydrogen using a catalyst. Okay, what is the product? Right. Okay, so the product will be butane. And even if we had just one equivalent of hydrogen, it would be very difficult to stop at the alkene. It just keeps going if you have a nickel, palladium, or platinum catalyst. Okay, so what is the product if we hydrogenate this with a Lindlar catalyst? And what is the stereochemistry of the product? Okay. So this will add just one equivalent of hydrogen. And this is stereoselective. You'll get the cis isomer. Okay, in order to make the trans isomer, we would use sodium in liquid ammonia. Okay, that is distinct. It's different from what we saw a few minutes ago, NaNH2 and ammonia. Okay, this time it's just sodium metal. Okay, I'm going to erase this and start over so I have more room for the complete mechanism. Okay, we have U2-ine. First, what happens is we have sodium metal. Okay, I've got a little dot there to indicate an electron. Right, in liquid ammonia, this will ionize. And the ammonia will solvate the free electrons. Okay, and then this electron will attack one side of the alkyne. Okay, notice the single barbed arrow, that's to indicate just one electron. Okay, that will attack one side, and that's going to push a pair of electrons over to the other side. Okay, because excuse me, because this orbital and this orbital take up a lot of space, they need to be trans to each other. Okay, and then what happens next is right, this will take the hydrogen from the ammonia. Right, then another electron. Okay, this process, another sodium loses an electron. Okay, so that will join the single electron. Okay, since we added an electron, this is now negative. All right, this will then remove another hydrogen. And so our final product will be the transbutene. Okay, I'll just have you do product on this one. Okay, propine. And let's react this with two HBRs. That's HBr without peroxides. You think about Markovnikov's rule, the rich get richer when it comes to hydrogen. Got two equivalents of HBr. Okay. Product will be 2,2-dibromopropane. Okay, both hydrogens will go to carbon number 1, both bromines will go to carbon number 2. Again, what is the product?
Is that HgSO4?
That is Hg, yeah. So mercury 2 sulfate, sulfuric acid, and water. Okay, these catalyze the reaction, but it's actually water that adds mercury 2 sulfate. Right, so for an alkene, we would add H and OH. This follows Markovnikov's rule. Okay, this is an enol. Okay, if I add H here and OH here, most enols are not stable. Okay, so this will rearrange, and an enol becomes a ketone. Okay, these are not resonance structures because hydrogen is moved.
Wait, Dr. Trump,
Yes.
could you show the mechanism for the formation of the enol? Or do I not have to know that?
I don't think that's actually given in the textbook.
Okay.
I can show the mechanism for this last step.
So I don't have to know the mechanism for the formation of the enol? No, I just have to know the mechanism for the last step, yeah.
Just asking for that product here.
Okay.
Okay, but the formation of the ketone. Okay, this hydrogen is especially acidic because of the nearby alkene. This would take a hydrogen. Okay, so this would rearrange the ketone. And the equilibrium overwhelmingly favors the ketone. Okay, so this is dicyanylpurane. Okay, I'll write that out. This is dicyanylpurane, followed by hydrogen peroxide and OH minus. Okay, and the main clue here is the boron. Okay, think about alkenes. We use BH3THF. Okay, here we're using dicyanylpurane. It's a hindered borane, bulky borane. It only has one hydride equivalent. Okay, this will be anti-Markovnikov. Okay, so again, this is an enol, and this enol is not stable either. Okay, so this will rearrange to the aldehyde. Okay, so whenever you have a terminal alkyne, you'll get an aldehyde with these reactants. If it's an internal alkyne, then you'll get a ketone. You'd actually get the same product as if you used mercury 2-sulfate and sulfuric acid and water. Okay, so this adds H and OH. Gives you the anti-Markov addition product. Okay, the next one. Okay, cold dilute amino-4. Okay, this is just product. All right, with an alkene. Okay, remember we got a diol when we did this. Okay, so what we'll get is a diketone. Okay, initially, we'll get this compound with 4 alcohol groups, but then we'll lose 2 water molecules to get the diketone. Okay, what if we use warm KMNO4 or ozone? What would happen then? Okay, this would completely cleave the triple bond. We would get 2 molecules of carboxylic acid, and since this is symmetric, they would be 2 molecules of the same carboxylic acid. Okay, there is a subtle difference if the alkyne is terminal. So with ozone, split this. Okay, so with ozone, one of the products is formic acid. Okay, with KMNO4, okay, that N carbon would go all the way to carbon dioxide, and then you'd also have water. Okay, but for internal alkynes, the products would be identical whether you use KMNO4 or ozone. Okay, what if we use 2 equivalents of Br2? What would the product be? Right, it would be 2233 tetrabromo butane. Okay, and then we could go the other direction. Okay, in other words, go from this to this using zinc metal, 2 equivalents of zinc metal. Okay, a lot like we did in lab, except we used a dibromo to go to an alkene. Okay, so this does an E2 elimination twice. That would take you back to the alkyne. So alkynes are usually prepared from halides using elimination reactions. We had two dibromobutane. Okay, the alkyne that we prepared would depend on what base we use. Okay, so if we use KOH at about 200 degrees Celsius. Okay, so we take the KOH solid and we melt it. Right, this would favor the internal alkyne. Right, so the mechanism is just your straightforward E2. So this takes a hydrogen, we form the double bond, we kick out the bromine, and then we do that again, and we get the alkyne. Okay, so with KOH, if more than one alkyne can be formed, the internal one is favored. Okay, but go ahead and erase this. Okay, so starting with the same dibromo compound, if we use NaNH2 at 150 degrees. Okay, this is different from the reaction we had a few minutes ago. That was NaNH2 in liquid ammonia. Liquid ammonia is something like minus 35 Celsius, somewhere in that range. Okay, this is 150 degrees Celsius. Okay, this will also do, let's see, that for that last mechanism, I guess I should have taken one of these hydrogens to get the internal alkyne. Okay, so KOH gives you the internal alkyne. NaNH2 is going to give you the terminal alkyne. In this case, we have a second step here where we add water. Okay, so NaNH2 will give us the terminal alkyne. Okay, as far as some useful products from alkynes, probably the most commercially abundant is acetylene or ethine, and it's used in cutting and welding when it's mixed with oxygen. It gives a very hot flame. There's a lot of energy stored in that triple bond. Okay, there are some drugs, anti-cancer drugs, for example, that contain the triple bond. There's a compound called phenyl estradiol, which is a contraceptive. So I'm going to go ahead and stop here. We're just about out of time. And on Friday, we'll take a look at reviewing chapter 10. Okay, as far as lab, okay, I have 4 videos that are posted in a folder called lab videos. And okay, so I want you to watch those videos. One of the difficulties I have as far as problem sets is that we have 2 students that aren't enrolled in lecture. So what I'll probably do is assign the mastering problems for IR and NMR, and that would just count toward your lecture grade. Okay, so I'll see you on Friday. So tomorrow, if you haven't already, go ahead and watch the spectroscopy videos.